Welcome to the module on lipids. In this lecture, we will cover the following topics. We will go over the definition of lipids, their types, which include sterols, galactolipids, glycerolipids, and sphingolipids. Then we will talk about fatty acids, and then about the double bonds position and orientation and their effects on lipids. And finally, we will cover fluidity. Lipids are a large group of naturally occurring compounds that are chemically diverse. Their main and defining feature is their insolubility in water. When first discovered by Michael Eugene Chevreul in 1814, lipids were referred to as margarine, which is Greek for pearl. Chevreul believed that the characteristics of this new compound resembled the appearance of mother of pearl. Lipids we cover in this class are membrane lipids, and all are amphipathic molecules. The definition of amphipathic is having both polar and nonpolar regions, such as lipids with polar heads and fatty acid tails. This central feature of membrane lipids is what dictates the arrangement of lipids molecule in a biological membrane. Membrane lipids are arranged in a double layer where the hydrophilic polar regions are exposed to the cell and its surroundings, and the hydrophobic nonpolar regions are located between the two layers. This arrangement acts as a barrier to the passage of polar molecules and ions. Lipids compose 5.9% of a leaf's dry weight. Among this percentage, almost 57% are glycerolipids. Lipid types distribution differs according to the tissue they are present in. The difference is mainly due to the cell membrane function at the specific site. In this section, we will cover four main types of lipids involved in membrane structure. Glycerolipids, in which the hydrophobic regions are composed of two fatty acids joined to a glycerol, and galactolipids, which also contain two fatty acids esterified to glycerol. Sphingolipids, in which a single fatty acid is joined to a fatty amine, sphingosine. And sterols, compounds characterized by a rigid system of four fused hydrocarbon rings. Sterols are amphipathic molecules with a fused four-ring carbon structure in their hydrophobic tails. A familiar example of sterols is cholesterol, which regulates membrane fluidity. Much of the cholesterol molecules intercalate into the bilayer, decreasing the permeability of the bilayer to water. When cholesterol intercalates between lipid molecules, it fills the free space and decreases the flexibility of surrounding lipid chains. In galactolipids, one or two galactose residues are connected by a glycosidic linkage to the C3 of a 1,2-diacylglycerol. Galactolipids are localized in the thylakoid membranes of the chloroplasts. They make up 70 to 80% of the total membrane lipids of vascular plants. They are probably the most abundant membrane lipids in the biosphere. The third type of lipid we'll cover is the glycerolipid. These lipids are based on a glycerol backbone consisting of 3-carbon triol. The glycerol can attach up to 3 fatty acid chains by ester bonds, forming a triglyceride or a triacylglycerol. Triacylglycerols are primarily used for storage. Plant membranes usually have glycerolipids with 2 of the positions filled with fatty acids, forming a diglyceride. Diglycerides are the main membrane lipids. Most diglycerides have polar head groups, including either a phosphate group for the phospholipids or a sugar or sugar derivative for the glycolipids. Monoglycerides have a fatty acid only esterified to the SN1 or 2 position of glycerol. They are rare in biological systems. Carbon positions on glycerolipids are denoted by stereospecific numbering or SN position. Here we see the SN1 carbon or end carbon with a saturated fatty acid and the SN2 carbon or the central carbon with an unsaturated fatty acid. SN3 is the end carbon, often attached to various groups designated by Y and X in the diagram. The fourth type of lipids we're interested in are the sphingolipids. Sphingolipids have a polar head group and two nonpolar tails, but unlike glycerophospholipids and galactolipids, they contain no glycerol. The backbone of sphingolipids is similar to glycerol, but the numbering of the carbon is reversed. The number 1 carbon has various attachments. The number 2 carbon has a fatty acid at the amino group, and there's a built-in nonpolar tail at the number 3 carbon, which is sphingosine in this example. Revisiting the last two types of lipids, we can see their similarities. Two lipids based on glycerol are on the left, and the one on the right is based on sphingosine. As we can see, various attachments are found at the SN3 carbon in glycerides and at the SN1 carbon in sphingolipids. These attachments encompass carbohydrates, phosphate, and amines. Carbohydrate attachments such as glucose and galactose are often found in plastids. Be careful not to confuse the terminology, which can be based on the backbone or attachment. For example, many lipids with a sugar attachment are also glycerolipids, which are lipids with a glycerol backbone. The phosphate in phospholipids usually has its own attachment. Fatty acids comprise the hydrocarbon tail in most lipids. Most of the fatty acids found in plants have 16 or 18 carbons. The number of double bonds can vary from 0, which represents a saturated fatty acid having a straight chain, to polyunsaturated, which have a number of double bonds that can result in kinks in the carbon chain. The number of carbons and double bonds, as well as double bond position, dictates the nomenclature of the fatty acid. For example, an 18 carbon chain with 0 double bonds or saturated is a stearic acid. 18 carbons with 1 double bond is oleic or cis-9 octadecanoic acid. 18 carbons with 2 double bonds is linoleic. 18 carbons with 3 double bonds is linoleic acid. An example of saturated fatty acid with 16 carbons is palmitic or hexadecanoic acid. The position of the double bonds is indicated by a delta symbol. Our example here is linoleic acid with an 18 carbon chain with 3 double bonds at the 9, 12, and 15 carbon. Our frame of reference for numbering comes from the carboxyl carbon, which is designated as carbon number 1. Double bonds can have the rest of the molecule, sometimes referred to as the R group, on the same side or the opposite side of the double bond. If both R groups are on the same side, the chain bends and is referred to as the cis orientation. A trans double bond or a double bond with R groups on opposite sides is pretty straight. This is another diagram illustrating the differences between cis and trans bond orientations in fatty acids. Most fatty acids in plants are cis. Trans fatty acids are rarely found in nature, which is one of the reasons trans fats are a health concern with artificially hydrogenated oils used in food industry. Double bonds are important because bends restricts packing. Unsaturated cis fatty acids make membrane more fluid. Maintaining optimal membrane fluidity is a key to a functional state. If the membrane gels or becomes hyperfluid, its properties will change. The following video is a cool demonstration of membrane fluidity in an animal cell.
To demonstrate the fluidity of the lipid bilayer, a piece of the plasma membrane of this neuronal cell is pulled out with laser tweezers. Remarkably, moving this membrane tubule rapidly back and forth does not rupture the plasma membrane, which flows quickly to adapt to the mechanical distortion.
In this table, we see the different melting points of lipids based on head groups, number of carbons, and presence of double bonds. You will recall that most membrane lipids are diglycerides with two fatty acid chains. Tm stands for melting temperature or the phase transition temperature. In this instance, the melting temperature is the point where the fluid membrane solidifies into a gel. We have an example of 14, 16, and 18 carbon chains. The head groups are phosphatidylcholine, PC, and phosphatidylethanolammine, PE. We can see the fatty acid chain length affects melting temperature with the shorter tail staying fluid at lower temperatures. The 18, 16, and 14 carbon lipid species melt at 55, 42, and 24 degrees Celsius respectively in PC. This is quite a significant difference. Add a double bond to the 18 carbon chain, and the Tm changes from 55 degrees to minus 22 degrees. This is a difference of 72 degrees. The size and charge of the head group also affects Tm. PC is bulkier than PE, so it doesn't pack as well, which keeps it in a fluid state at cooler temperatures. These different properties between lipids can optimize membrane fluidity by altering membrane composition as temperature demands. At the end of this lecture, you should know the answers to the following questions. What do we mean by amphipathic? What are the major types of membrane lipids? Give an example for each type. What is SN position? How does the double bond position affect its orientation? How does the double bond orientation affect the membrane fluidity? How does the double bond presence affect the physical characteristics of the molecule?